it's time to get underway. So welcome everyone back to the Asia Pacific Analysis and PD seminar. Seems a little superfluous for me to be introducing today's speaker, since Daniel is really the father of this seminar in a way. Back in the dark days of the pandemic, when we needed it most, it was his idea to come up with this seminar series. Today, he's going to, I should say, perhaps this is also perhaps something of a farewell or a swan song, we should say, because Daniel will be leaving Australia soon to a position in Germany. So particular pleasure to have him speak to us today. The title of his talk is An Extension Problem for the Logarithmic Laplacian. Thank you, Daniel.
Thank you, Ben. It's a great pleasure for me to give a talk in this beautiful seminar. We will, even so that I'm taking on another position in Germany, I try to keep going this seminar and keep connected with the Asia-Australian region, and to continue at least on a monthly basis this nice seminar series. I was asked by Professor Yoshikatsu Giga and also by others that we should keep running this seminar even so we are not anymore in this pandemic. And I will do my best to keep going, basically, and even from far away. So today I want to speak about a problem which is actually a follow-up work. So where you can really see the fruits of this seminar. So we had in the 27th of June, I just have it next to me, in 2022, a first talk on a similar topic. It was given by Alberto Saldana, who was a research fellow at Universidad Nacional Autónoma de México, and he spoke about the asymptotic analysis of fractional problems via the logarithmic Laplacian. And for me, it was a very hot topic currently in this non-local analysis community, or non-local in this PDE community, which have non-local operators involved. And I asked him the question whether there's not an extension property available. And so in April this year, I visited Tobias Weth at the Goethe University in Frankfurt, and then we started discussing and working on this problem. And then Huyan Chen, who's a former postdoc of Tobias Weth, joined him and also joined the project. And now we are almost ready to submit. So this is now really a follow-up, and how we can see it's really fruitful that we always present our results in this seminar, and then we can profit from the project of the others, discussions, and so on. So, as I said, this is joint work with Huyan Chen from Jiangxi Normal University, who is also currently at the University of Sydney since the 1st of December, and with Tobias Weth from the Goethe University in Frankfurt. So let's start slowly first, and let's see, and then we come at the end to the main result. And just that you see, I mean, I will not give you the rigorous proof of the result because there would be many integrals involved and many estimates, but I want to give you a derivation of this property of the logarithmic Laplacian. So starting with the fractional Laplacian, so this is a non-local operator which fractional powers s between 0 and 1, and for every sufficiently smooth function, here for instance C2C, the fractional Laplacian can be defined as this Cauchy principal value, but in fact we know there are 10 different ways meanwhile to define the fractional Laplacian on the whole space Rn. However, since we are now here in a PD talk, the singular integral is the most useful notion. And here this constant CNS is a uniform estimate which is given in this way. You can compute it, or give it explicitly. And in particular, when you want to compute the logarithmic Laplacian, you must control all these normalization constants. So, as I already said, there are 10 different ways to define the fractional Laplacian. The fractional Laplacian can also be obtained basically as a pseudo-differential operator, which has a Fourier symbol, absolute value sine the power of 2s. But then u needs to be, again, a smooth function away from zero, so that it becomes basically a pseudo-differential operator. So we know very well the following properties, and that is the following. So when you take S tending to zero, then the foregoing normalization constant CSN was basically chosen in such a way that when S tends to zero, then you can recover U of X. And when S tends to 1, then you recover the local operator, which is the negative Laplace operator. Motivated by this fact, Huyan and Tobias, they thought, okay, let's define the logarithmic Laplacian as basically the first variation of the fraction Laplacian at S equals 0. Okay, so that's really is the first variation. And then they came up with the following nice result. So when U is in C alpha, so Holder continuous with compact support, since you take S going to 0 in the derivative of the fraction Laplacian, so here really this is a derivative with respect to the parameter S at S equals 0, then it's sufficient to have U just Holder continuous, because the singular integral will actually exist then, since you let S going to 0. And the surprise was that they get actually that this limit exists, and pointwise when U is Holder continuous in compact support, and also you can actually you obtain a principal value notation, and that is that the logarithmic Laplacian is equal to this uniform constant Cn, which is this one, of the limit when epsilon goes to 0 of Rn minus the ball of centered at x of radius epsilon of U of X. And here this is the identity for Y at the unit ball centered at X minus U of Y, plus some number rho n, which you can compute explicitly in this way, times U of X. Okay? And a surprise was, if you take sufficiently smooth U, this kind of operator has also a Fourier symbol, and that is 2 times the logarithm of the absolute value of psi. So I think this is a very big surprise, basically, that you still can get such a singular pseudo-differential operator from this. Okay, and let me explain you why this is actually, so there's different kind of functional calculuses in functional analysis, and one is the Bernstein functional calculus. So for instance, fractional powers, that they have, a Bernstein function is easy because it's basically the fractional power times a positive accretive operator, and so everything is nice. But the logarithm itself is not anymore a Bernstein function. You know, everyone knows that ln of lambda is divergent to minus infinity when lambda goes to 0. So that's the reason why such a calculus is really a big, actually, surprise. The reason why Tobias Weed and his collaborators came up with this was because they were always interested in the asymptotic behavior for Dirichlet eigenvalues and eigenfunctions of the fraction Laplacian when S is close to 0, basically. And other people, as also, for instance, Saldana was also in this direction as asymptotic behavior interested. But later, other groups like De Luca, Novaga, and Ponciglione, they came up that actually the logarithmic Laplacian has some relation, to some geometric context, and that is the 0 fractional parameter. So an independent discovery was as well. So it occurred in a study by Frank Rupert and Tobias König and Tang by the study of the Euler-Lagrange equation of a conformally invariant logarithmic Sobolev inequality. And so you see that actually this new object, the logarithmic Laplace operator, is really an important operator which occurs in several applications. So what is a major, and so therefore actually it's really interesting to know what kind of properties this logarithmic Laplacian has. So we know already from the fraction Laplacian that since the paper by Caffarelli and Sylvester 2007, that for every function u which is sufficiently smooth, you can extend u from Rn to the half space, so the upper half space, and you can extend it such that it is actually an S-harmonic extension. So this means Ws is a distributional solution of this Dirichlet problem. So the boundary of the half space is of course Rn. Yeah. And so really you see now here, U is extended by Ws on the half space, and Ws in addition has a property to be a weak solution of this singular divergent second order differential operator. And then the surprise was that the co-normal derivative of this operator, the co-normal derivative at the boundary, that is this guy here with the minus, is equal up to a multiple constant ds, the fraction Laplacian of u. Yeah. So there's other papers who reprove this, and actually they gave really the functional analytic framework to this important result. One is here in the audience, and this is Tom Elst, together with Wolfgang Arendt. But there have also many other people like Stinger and his collaborators who revisited this famous result by Caffarelli and Sylvester and provided and developed actually this functional analytical framework. Okay, so as I said already, in this, because of this result, one can see the fraction Laplacian as this operator lambda s up to a uniform constant ts, multiplicative constant, and this lambda s is the Dirichlet-Neumann map associated to this singular second order differential operator on the half space. So, and now this was basically our starting point. We wanted to know whether a similar property is also true for the logarithmic Laplacian, which I introduced just before. So the starting point when I came in April was that we tried to do actually, we studied the asymptotic behavior of the solution of the Dirichlet problem when S is very, very small. So the nice thing is that this solution of the Dirichlet problem on the half space, so Ws, has actually a Poisson kernel. So Ws can be represented exactly as this integral, yeah, for any boundary data u. And this PNS is again a uniform constant which one needs to control, and therefore I give this constant explicitly, and this is given in this way. Okay, so now what you can do is you can actually you can simply you can actually solve the Dirichlet problem not only on the half space by simply extending the solution. You make it by simply taking the absolute value of t. You get actually a solution on the full space Rn plus 1, and then the boundary of Rn plus 1 would be again Rn. So what you obtain is then that Ws, I identify it again with t, but now I take absolute values here, is again a solution of this equation, but on Rn times t, but of course not at t equals 0. Okay. So, and now what we are looking is, we look now for the asymptotic behavior of Ws when S becomes very small. But we are not only interested on Ws. When you remember actually what was the logarithmic Laplacian, the logarithmic Laplacian is the first variation, so the derivative. So what you have to understand is what happens with basically the differential quotient when S becomes very, very small. And so what we figured out actually is that this quotient here, this 2 is just the normalization constant, so don't worry about it. But this quotient actually is bounded when S becomes very small. And so it makes sense to rewrite denote this quotient at Vs. And then for s very small, we can make now the following ansatz. So we can rewrite Ws in this way, where Vs is a bounded function when s becomes very, very small. Okay, and then you can actually use properties of Ws in order to figure out properties of Vs, actually. This is a very useful ansatz. Okay, recall that now the fraction Laplacian is the Dirichlet to Neumann map up to a uniform constant ds. Yeah, so in fact, this means that the fraction Laplacian at u of x is minus the uniform constant ds of this co-normal derivative of Ws. So if we now insert this asymptotic ansatz in this limit, then we first compute, of course, this part, t in the power of 1 minus 2s times the partial derivative. We can do this. The partial derivative can be written exactly in this way. And then we multiply it by t in the power of 1 minus 2s. And then you see that those terms actually, here t in the power of 2s minus 1, they get cancelled. They're just 1. And now we can look for the limit, basically. So this means when s is very, very small, but still positive, the fraction Laplacian can be written as the limit of this, what is written in this round brackets. Okay, for s very, very small, but positive. Okay, so now you can actually rigorously check this condition t times wtvs. It exists exactly because the co-normal derivative of, because this limit here exists. So this is really the reason why when I take t to 0 of t times partial tvs, that this limit would exist, and this limit is actually 0. This is because of the previous limit exists. So this one can check rigorously, basically. So this is nothing less than a L'Hopital's rule, actually. And so when I take this limit, what I get is that I actually obtain exactly this. So the fraction Laplacian of u of x minus u of x, I add this simply, minus, and now I took the limit of this, and this is then 2s ds minus 1 of u of x, minus s squared times vs. So this is simply still this here. Where I assume that, of course, vs is continuous for t equals 0. Okay. And then, so now the next step is we divide by s. So now we have the differential quotient. Okay, and so the differential quotient for small s becomes exactly this form. And now you see here occurs this uniform constant, which is in front of the characterization of the fraction Laplacian. Yeah, so this was the uniform constant in front of the Dirichlet to Neumann operator. And now you need to know, since we know when u is Hölder continuous, we know that when s tends to 0, this limit, when s tends to 0, will exist, but still we have to verify, of course, what happens with this quotient actually. Yeah, and what happens actually with this part. So what happens with ds times s? So luckily, you can compute it explicitly that the limit when s tends to 0 of s times ds is just a half. And the limit when s goes to 0 of this quotient, when you compute explicitly, is just this here. And this is 2 times ln 2 plus 2 times gamma dash of 1, where gamma dash of 1 is related to the Euler-Mascheroni constant. So both limits exist. And so now, if we make now, because this is just a formal derivation, let me make an additional assumption. As I said already before, I need to know whether v of 0 is continuous at t equals 0. I need for this derivation, I need to make now the following assumption, that there would be a v which is continuous on Rn plus 1, such that Vs locally uniformly would converge to V naught for every bounded set B or compact set C in Rn plus 1. Okay, if I do this assumption, then I get basically exactly that this holds here. Yeah, so the right hand side, the logarithmic Laplacian of u, which is the limit of this, is exactly this part. And now what misses is I need to get information, or I need to identify what is V naught. Once I know what is V naught, I have exactly the characterization, an alternative characterization by the right hand side, this side, of the rigorous definition of the logarithmic Laplacian. So let's do this. Let's identify V naught. That's the next step. So again, we get information on V naught, all of course from the fractional power case. So one very interesting observation for me at least was that, okay, if you look in the sense of distribution on Rn plus 1, then the Neumann condition, so you saw that Ws is a weak solution of the Dirichlet problem, and the fractional Laplacian is the co-normal derivative of this extension. This you can summarize actually in one line. You can see that this equation is actually a Poisson equation on Rn plus 1 in the sense of distribution. And on the boundary, you get the Neumann condition, and this is 2 divided by ds of the fractional Laplacian u, where we have here, you must think about this in sense of distributions. So these are measures. So this is the product measure of the Lebesgue measure times the Dirac, and that is the variable t. So the second one, so if x is the variable running through Rn and t is the variable which runs in R, so then this is basically the product measure of the Lebesgue measure times the Dirac measure t equals 0, at t equals 0. Okay, so you can then rigorously compute that Ws is exactly a distributional solution in Rn plus 1 of this Poisson problem. Okay, which really means for every test function C infinity with compact support, you get, when you swap the differential operator on phi on the test function, this is equal to 2 divided by ds of this one. So the 2 comes, let me just explain this, because we said Ws is basically through reflection on the left-hand side of the half space. And so what you're doing is you're hitting the Neumann condition from left and from right. And therefore, the Neumann condition appears twice. And therefore, you have this 2 here. Okay? So, and remember, Vs was exactly this quotient. And so the next step is basically to know what kind, knowing that Vs solve is a solution, distributional solution of the previous Poisson problem, what kind of distribution solution is Vs? And in fact, you can check this rigorously. Vs is the distributional solution exactly of this right-hand side, so of the whole equation, but this so minus divergence of absolute value t times the gradient Vs. Note the gradient is respect to x and t, and then it solves basically the right-hand side is exactly given in this way, where t divided by absolute value t is the signum, depending where t is on Rn plus 1, if t is positive or negative. And here again, here you have the product measure of the Lebesgue measure with the Dirac measure. And I see here is an absolute value missing. Excuse me. Okay. So this means, in the sense of distribution, we have exactly this equation. So, and now, of course, we want to let s tends to 0. Yeah. And now, if we use that the fractional Laplacian here minus delta s of u, when s tends to 0 goes to u of x, and since we have assumed that Vs converge locally uniformly to V naught, this is sufficient in order when we have this integral equation by a test function, we have basically localized it because phi has a compact support. And so when we now let S tend to 0, this integral equation simplifies and simplifies more. In fact, the left-hand side minus 8 times this one cancels with the right-hand side. And so what we have shown is that V naught is a distributional solution of exactly this equation in Rn plus 1. So this is very useful. And so now remember what we do now as next step, we use exactly this limit. And now we introduce a new function, and that is, we say Wu is now just a quarter times V naught. We have identified V naught minus this term. This is in some sense, when t goes to 0, the singular part. It's like an excess term. And then we will see that this W is the distributional solution of this Poisson problem. And remember, so this means the right-hand side, when you write it in this way, because we are taking this in distribution sense on Rn plus 1, so you have a boundary term, because you have the product measure of the Lebesgue measure with the Dirac at t equals 0, that actually this solution is equal to 2 times u. So you have a Neumann condition, which is u. That is what you have. So let's check this. So we know we have defined W as a quarter V naught minus u of x, ln t. So the divergence will carry over because at times absolute value t and the gradient, since these are all linear parts, goes over on the other parts in the sum. And then what one can verify, we know actually a solution of this equation. Yeah. So the second part, the plus divergence of this term here, you have here 1 times the gradient with respect to x and 1 times the gradient to t. And you have here basically u just depends on x and ln of t, and t just depends on t. So you can basically, you get 2 terms out of it. And 1 term will be exactly this term here. This one you can compute explicitly, and this is 2 times the Dirac measure at t equals 0 in R. And so we get basically that minus of the divergence of absolute value of t times the gradient of Wu is exactly this term. And this cancels each other out. You see, this is equal to this one. And what remains is this. But the divergence with respect to t of this term is just 2 times delta. And so what we have proven is that W is a distributional solution of this equals this, in the sense in Rn plus 1. Okay, so let's summarize. Wu, in fact, so this equation 5 here is actually equivalent to saying, sorry, the W, when we just look at on the upper half space, so Rn plus 1 plus, that W is a solution of this differential operator, and the co-normal derivative is just u. Again, this 2 which occurs here is because we are on Rn plus 1, and so you come from left and from right to the boundary, and so you take the boundary data twice. So therefore, when you just look at on 1/2, you get really that W is a solution of this Neumann problem on the upper half space. Okay, so remember V naught is exactly this. This is how we define W. You see the quarter before is now we add here the 2. And why do we do this? Because we had in the first part, we have shown that the logarithmic Laplacian is given exactly in this term. So now what we simply do, we insert this limit where V naught was written. And so we can now provide the following characterization. The logarithmic Laplacian of U, when U is sufficiently smooth, is basically this uniform constant, 2 times ln 2 minus gamma, times the identity, minus 2 times the limit of this Dirichlet data of W plus an excess term, excuse me, plus this excess term, because when t tends to 0, this will basically explode and goes to minus infinity. Okay, so what we have shown here is formally we have justified that the logarithmic Laplacian is basically a uniform constant times the identity minus 2 times the Neumann to Dirichlet map with an excess term associated with this differential operator minus divergent t times nabla on the upper half space. Yeah, that is exactly what we have shown. So the nice thing is we can even derive, so what we have done is actually we have, as in the previous paper by Caffarelli and Sylvester, they have actually not only one derivation of this extension property for the fractional Laplacian. And yes, you can do exactly the same. We have actually 3 different proofs of this extension property for the logarithmic Laplacian. And but we basically in our paper we provide 2 formal proofs, and one is really rigorous with all a priori estimates and all justifications why the integral terms exists, why the limit exists, and so on. But we find actually this is also very nice. But another interesting point was that okay, you know, for the fractional Laplacian you have a Poisson kernel representation, and you could start basically proving this extension property also by the integral by the Poisson kernel representation out. So once you start, the WS is this Poisson kernel, you can insert it in this quotient. And I think there's a 2 missing, actually, I just realized. And then send S tends to 0. And what you get is actually you can prove then that V naught has exactly this integral representation plus 2 times ln t of u of x, which is again this excess term. Yeah, and so what you get is here, this is basically WU, which is the solution of the Neumann problem previously. So you get a Poisson kernel, of the Neumann problem as well for any given u. Okay. So now let's come to the main result. For this, we introduce the following space. This is L1 naught of Rn is basically L1 with the measure dx divided by 1 plus absolute value of x in the power of n. And if you don't need so much smoothness assumption, which I did in the formal derivation. So if now the Neumann data or the data of u is just in L1 naught, then one knows that the logarithmic Laplacian exists in a distributional sense. And therefore it makes sense basically to establish or try to establish this extension property as well for these kinds of functions. And indeed it worked. So we could show that WU, the solution of the Neumann problem, or this, there's a unique distributional solution which has this kind of regularity. And in fact, you can show even more, which I did not write here. WU has at most algebraic growth, okay? And which you can easily derive by the Poisson representation of W. And so W is a solution of this Poisson problem, which is equivalent to the Neumann problem on the half space. And it vanishes at infinity. And because of these vanishing condition, you get basically just one solution with this property, and this solution is a solution which has this Poisson formula. So the Poisson formula of W is given in this way. And you get that with this, so the extension can then map to Dirichlet data, and with this you can characterize in the distributional sense that the logarithmic Laplacian is exactly in this form. So this holds in the sense of distribution. And what you also can show that actually W divided by ln t actually converge to minus u of x in L1 log. So this we identify, so this is the asymptotic behavior when t is close to 0, but it's a kind of a strange, it comes from this excess term ln on t. Okay, so if you actually assume a little bit more regularity on u, so if you assume that u is also Dinier continuous at x, then you can show that this actually holds pointwise. So you get in particular that this limit is not only in the distributional sense, that this even holds pointwise in the strong sense. Okay, so there are some quite interesting applications of this. And so let me first stress again something concerning this characterization of the logarithmic Laplacian, and let me make here the following comment. So the distributional definition, or this distributional characterization of the logarithmic Laplacian, means that this integral equation is true for every test function phi. Okay. So, and in fact, what we also show is that this is not, we don't need, in fact, you see the logarithmic Laplacian of phi, it does not have actually to be in C infinity. The logarithmic Laplacian of phi just exists for Hölder continuous function, or even just for Dini continuous function. And so this characterization even holds when we replace phi to be in CDC. CDC, Rn is the space of uniformly Dini continuous function on Rn with compact support. So Dini continuous is a little bit more than continuous and less than Hölder continuous for those who are not familiar with Dini continuity. Okay, and so by using this property of the distributional characterization of the logarithmic Laplacian, we were actually able to derive easily an alternative representation of the energy function to the logarithmic Laplacian. So in the paper by Chen and Wade, when they first time introduced the logarithmic Laplacian, then they showed that the energy functional EL phi, which is actually just the inner L2 inner product, phi times the logarithmic Laplacian applied to phi, that you can rewrite it exactly in this term. So here really is the integral representation hidden of the logarithmic Laplacian, which was theorem 1 of them, which I mentioned at the very beginning. So if you use now our alternative way to define the logarithmic Laplacian, you get actually the following integral energy, which is associated to the logarithmic Laplacian. So this uniform constant, which was occurring in the characterization, times the L2 norm squared of phi, minus the limit of phi times exactly this term. Yeah. So of course, I mean, why is this interesting? So firstly, I think it's quite from the functional perspective, functional analytical perspective, it is interesting to see that the logarithmic Laplacian is related or can be derived using variational methods. So there is an energy functional basically associated. I think Ben Goldis would immediately ask me. So these energy functionals are also important in order to know whether there are Hunt processes can be generated, or which again imply basically the existence of a stochastic process. And so now, but this alternative way, basically, one could actually conclude whether there maybe would be a monotonicity formula known, or is a frequency result related basically to this logarithmic Laplacian. So far, we don't know, but at least there are the first Ansätze, which goes basically in this kind of direction. And I think this is quite interesting to follow up concerning the regularity and so on. So another interesting result is also that if U is basically a solution of this, let me come up with this again. So if WU is the weak solution or the distributional solution of this Poisson problem, then actually what you can do is you can double up the variables. So let's see. So first you see basically Rn as a function in Rn plus 2. Okay. And then what you see is when you double the variable, then you get basically that W, you reduce here the modulus in the divergence, and you see that actually harmonic functions are related to the logarithmic Laplacian. Okay, so away from the case Rn cross 0, 0, you have actually that W is an harmonic function on Rn plus 2. And only the boundary, so where the Dirac measure heads here, there you get basically that the Neumann condition is 2 pi times U. And this is the fact because, I mean, this divergence here is x and t dependent. And so you have two terms. You have the x dependent operator and the t dependent operator. And the t dependent operator is nothing less as the radial Laplace operator. And the fact that you basically now double the variables, you go one dimension up, and then you recover basically just the Laplacian. And this gives you then shows you that W is in fact an harmonic function. I find this also geometrically very nice because everything what is behind the logarithmic Laplacian, that there are actually harmonic function behind, this gives someone a very nice relation. So how do you show this property? Well, you start with a test function in Rn plus 2, and then you introduce this auxiliary function, phi tilde, xt. I see I don't actually have too much time anymore. Maybe we can discuss this later, but let me come to an application of this. Once you know you have harmonic function, what you can show is actually a weak unique continuation property. So if U is now the boundary data, and for any open subset omega in Rn, if U is 0 on omega and the logarithmic Laplacian is 0 on omega, then you can conclude that U needs to be 0 in Rn. And this is because by doubling the variable, you get harmonic functions. And since U is 0 on omega, this harmonic function will be also at T0, basically 0 on omega. And from this now, when you have harmonic functions, you can develop in the power series. And so you can use the unique continuation principle of the harmonic functions in order to conclude that U equals 0, basically. And I think my time is up. Thank you for your attention.
Thank you, Daniel. Very interesting talk. Okay, so I think people can ask questions by posting them in the chat. Or you can raise your hand and we can unmute you, I believe. So please feel free to do that. Daniel, I was interested in this expression you have for the energy, where you seem to have appearing there, not the energy and also the sort of integral expression for the operator. There's something like the difference of U from its average on the ball of radius 1. There's some sort of funny scaling there, right? So why do you get the radius 1 and not some other radius appearing here?
So
and if you rescale the whole problem, why do you not end up with a different radius? I don't quite understand how that works.
About it here, is it here in LNT or where is it?
No, in your expression for the energy, and right at the beginning, and also you had an expression, not your new expression, but the old one of the old expressions for the
this one,
the operator as an integral. Yeah, you get these integrals over balls of radius 1 here.
Yeah, that's true. Yeah.
Is that, I don't quite see how that scaling comes up. Is there some explanation for that?
In fact, it is okay. You could have written it actually in the form how I wrote it in the beginning. I wrote it with the indicator function on the ball of unit 1, but it is in some how they came up with the scaling. I cannot tell you basically. So what you do in order when you start from the fractional Laplacian, so it comes not naturally up actually. So is when you study the Cauchy principal value for the fractional Laplacian, you have the integral over Rn minus the ball centered of x. So what you do is, this is x minus x tilde. And now what you do in order to pass to the limit when s goes to 0, you basically divide different sections. So this would be, you divide Rn in a ball of some radius, for instance, radius 1, and then you look for the outer region, basically. And you have, and that is why, and then you check when s tends to 0, because you see there's not anymore n plus 2s there, there's just n. You need basically be able to control that this integral still exists. And that is, so this 1 could be also any other radius basically be.
Okay,
but
that answers my
really
question.
when you pass to the limit when s goes to 0, that they have divided Rn in 2 disjoint regions. One where this is close to the singularity, or not close, but here they really focus what happens when x minus x tilde becomes 0, the difference, and one when it is not so singular.
Okay, that makes sense. Thank you. Yeah. Very good. Are there any other questions? I don't see any hands raised or questions posted. Yoshi, firstly, Giga.
Yeah, very nice talk. Yeah, do you hear me? Okay.
Yes.
I have a very basic question. This logarithmic Laplacian, does this logarithmic Laplacian have some maximal principle like other fractional Laplacian?
That's a good question. I don't think so. This has been done yet, I must say. So this is actually not that straightforward. In order to prove the maximum principle of this, the extension property has been used, I think, in the first instance. And then later on, they came actually up maybe with some other integral inequalities. So I think this is to be shown as far as I know.
Thank you very much. Yeah.
Okay, very good.
Let me just make one comment to the maximum principle.
Yeah.
I mean, you use your maximum principle also to show some Lionville results, for instance. And so let me just add to this. So we use basically the fact that when we double the variable, that we get harmonic functions, and then we use the classic Lionville result in order to prove the uniqueness. I think it's possible to do maximum principles, but I am not sure if this has been done already.
Right, that's an interesting question, right? So then it's not so obvious there, because you have an inequality only on an n minus on a codimension 2 set, right? In Rn.
Exactly.
Rn plus 2. Yeah, interesting. Very good. Okay, so I should remind everyone that there is a coffee break if you would like to come along and discuss more informally. The details you can find in the email about this webinar. So please feel free to come along and join us in a few minutes. Just follow the link in that email to join the coffee break. If there are no other questions at the moment, then I'd just like to thank Daniel one more time for a very interesting talk. Thank you. So of course you can't applaud, most of you, but we'll take it as read. Very good. So thank you, everyone. And for those who would like to join us, please do so at the coffee break.
Okay. Thank you.